Okay, here's the notes for section 8.3, which is the volumes. So this is the thing about volumes of an integral. So the volume of a solid of known integrable cross-sectional area A of x from x equals a to x equals b is the integral of a from a to b. So volume is the antiderivative of the area. So method of slicing. So you want to sketch your solid, typical cross-section, find a formula for the area of that cross-section, find the limits of integration, and then integrate to find the volume. So example 1, pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the period parallel to the base is a square. Find the volume of the pyramid. So what it's saying is that you've got a square-based pyramid, and if you slice it any place, you get a square. So the sides of the square are x. So the area, so our area equation is just x squared. So x, though, varies. At the bottom, x is 3. At the top, x is 0. So if I want the volume, my side lengths range from 0 to 3. Area equation, dx. So what that's going to look like when we actually work it out is going to be 1/3 x cubed when we do the antiderivative. Or we can let our calculator handle it, but this one's relatively straightforward. So this is going to be 1/3 x cubed from 0 to 3. So that's 1/3 times 3 cubed minus 1/3 times 0 cubed. So that's 1/3 times 27 minus 0, so 9. So volume is meters cubed. These are units in meters. So this square-based pyramid has a volume of 9 cubic meters. All right, you can also have circular cross-sections. So that was a square. So this is the region between the graph of 2 plus x cos x, and the x-axis over the interval -2 to 2 is revolved around the x-axis to generate a solid. Find the volume. So what's happening is, if you look at your axes, from -2 to +2, so the curve looks something like this. So what you're doing is you're rotating it about the x-axis, so you're essentially making like a vase shape. That's really bad, but this should be a mirror of that. So if we slice this, we're actually going to get circles everywhere we cut it. Well, the area of a circle is pi r squared. The problem is the radius of this circle changes depending on where I slice it. But the radius of the circle is always equal to this edge, which is given by that formula. So the area equation is pi times the equation that gives me the edge squared. Now we go from -2 to +2. So when you set up our integral from -2 to +2 of pi radius squared dx. And then I'm going to let my calculator do this. So the integral of pi quantity 2 plus x cosine x squared from -2 to +2 gives me an area of about, or sorry, volume of about 52.4 units cubed, since it doesn't actually tell me my units. Okay, so let's look at this one. Example 3. The region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine x and y equals sine x, okay, is revolved around the x-axis to form a solid. So we're only looking over here. So cosine x does something like this, sine x does something like this. So we're looking at that area there. So these two guys meet, that value there is pi over 4. So our bounds of integration is 0 to pi over 4. Now, this one's a bit different because if I rotate it, I get this washer shape. If you have a washer, you take the outer curve and find the volume enclosed by it and then slice out the inside. So what that's going to look like, you can think about it as two things or as just one. So it is the antiderivative from 0 to pi over 4. So our outside shape is the cosine function. So that's going to be the volume enclosed all the way in here, but then I need to cut out that piece, which means I need to eliminate anything underneath the sine function. Now, since these have the same bounds, I should have done this the other way. I can write it as a single 0 to pi over 4 pi cosine x squared minus sine squared. So that reason squares show up there. It's there. All right, and then calculator time. So pi cosine x squared minus sine x squared from 0 to pi over 4. And this all comes out to be 1/2 pi. Units cubed. All right, so the region bounded by the graph 3, that should be a 3, should that be a cube root? Nope. 3 square root x over 4, the x-axis in line x equals 4 is revolved about the line x equals 4 to generate a solid. Find the volume of the solid. Okay, so let's see what we got here. So 1, 2, 3, 4. So here's our line, x equals 4. So x-axis is down here. Our graph, so when I plug 4 into this, 1, 2, 3. So our curve is going to do something like this. So we're looking at this area, and we're revolving it around the line x equals 4. So it's going to dome out over here. So circular cross sections are going to run left to right. So since our radii are in the x direction, I need to rearrange this so that x is by itself. So y equals 3 square root x over 4. So multiply both sides by or divide both sides by 3. So y over 3 equals a square root of x over 4. Square both sides, y squared over 9 equals x over 4. So x equals 4 y squared over 9, which is what's going to give us the radius. So our x values, let's see here, run from, or the y values are, sorry, since our equation has y's, run from y equals 0 to y equals this point here, which I said was what, 3? 3. So from 0 to 3 of pi, that's our radius equation, y squared over 9 squared dy. Okay. Nope, that's not right. The issue is that if we do that, we're measuring this distance. So since our axis is off the x-axis, we're rotating about 4. The bounds are the same, but our radius is actually 4 minus this equation. Okay? So this number here, you count back to your axis. If you reverse direction to get to your curve, you subtract your curve. If you keep going, you add. So 4, because I have to count 4 spaces back. I'm at positive 4, so positive 4. Okay, so this is actually our equation. And then this just happily goes into the calculator. So pi quantity, that's going to be squared again, because it's r squared. 4 minus, remember your calculator doesn't care what variable you use, so you can switch it back to x's. From 0 to 3. So this is 128 pi over 5 units cubed. So if you don't rotate about either the x or the y-axis, you have this formula. The distance back to the axis, and then plus or minus how long it takes. So minus if you reverse direction. So it's from here to here, it's 4 units. Then I had to turn around, so minus this. If you want to check when y is 0, your radius should be the full 4, which it is. When y is 3, it should all go away, which it does. Okay, cylindrical shells, region bounded by the curve, this, is revolved around the x-axis, generate a solid, find the volume of the solid. Okay, so what we've got, if you look at the graph, so we got root x, So here's x equals 4. This point is at 4, comma 2. This point here is at 0. We're revolving it around the x-axis, so here's our mirror down there. Okay. Find the volume of the solid. So we can also think about this in terms of a cylindrical shell. So the area of a cylinder is pi r squared h. So let's see here. Actually, I'm not sure I like doing it this way. So let me think about it. It's a better way to explain it. Yeah, so our cylinders are running this way, okay? So, oh, these are revolving, x-axis, okay. So the cylinder's height is given by 4 minus y squared. It's this distance here. The radius is just the y value. So this would become pi times y squared times 4 minus y squared. Okay, so no, it has a 2 pi out front here. So from our y values run from 0 to 2 pi. Oh no, we need the anti 2 pi RH. Sorry. It's 2 pi RH, not pi r squared. That squared's in the wrong place. So 2 pi r h. So that'd be the formula we'd work with, which I'm not sure if this is actually easier than just doing the solid of revolution, but that's me. So this comes out to be 8 pi. There you go, after all that. Okay, example 6, the region bound by the curves y equals 4x, 4 minus x squared, y equals x, and x equals 0 is revolved around the y-axis. All right, so let's see here. So 4 minus x squared, 1, 2, 3, 4, is a downward opening parabola. It's going to look like this. Y equals x looks like this, and x equals 0. No, this is the y-axis. So I'm looking at that region there. Find the volume of the solid. Okay, so the shell radius, so if we rotate it this way, the shell radius is just going left to right, so it's the x value. So let's see here. So 2 pi, the radius is x. The shell height is the difference between this curve and that curve, so 4 minus x squared minus x. Oh, okay, and we gotta evaluate. So x starts at 0, and we need to find that intersection point, because that's as big as the radius gets. And if you work that out, that's about 1.56 if you graph them and find the intersection point. And this all lovely goes in my calculator. And the number that comes out is about 13.3. So there you go. I personally do not like cylindrical shells. I would much rather prefer just to do the circular cross sections. This you'd have to break into more than one. All right, we found the example 5. Oh, all right, so this is actually what I was talking about. So here, so here's a curve, goes over here. This point is at 4, comma 2. We're gonna rotate it this way. So let's see here. So root x is our radius. So pi times root x squared. The x values range from 0 to 4. So, and we'll put this in our calculator. Dun-dun-dun. Pi root, oops. quantity root x squared from, 0 to 4, and lo and behold, a pi. Same answer, way less work. So I prefer to use solid revolutions as opposed to circular sections. Okay, last one. A mathematician has a paperweight made so the base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine x in inches. So what that's going to look like, be something like this. Okay. All right. So each cross-section cut perpendicular to the x-axis is a semicircular whose diameter runs from the x-axis to the curve. Okay. So let's see here. Oh, I get what I'm saying. All right, let's try to do this in 3 dimensions. So this is the base of the paperweight. So if you think about it, if that's lying flat, it's coming up above. Each cross-section perpendicular is a semicircle. So from here to here, so there are half circles whose radius is half this distance. So this distance is 2 sine x, but my radius is going to be half of that. Okay, so just sine x. Because the semicircle here, if this shape is the base, all the curves are centered here and they arc up. So our radius is just from here to here is sine x. So the area of a half circle is 1/2 pi, there's my radius, r squared. And this is going to range from 0, and this value here where it hits the axis again are pi. So all this goes in my calculator. Numbers come out is going to be 2.47-ish, and it's in inches, so inches cubed. The hardest part of these problems is drawing the figures and figuring out how it works. But that does bring us to the end of the section.